Hello my good people, and welcome back to my YouTube channel, Big Structural Hub, the #1 channel for structural insight. So today I want to talk about slabs, but I have not completed beam design. I'm only remaining with one question and then the summary, and I will be done with beam design. So let me introduce slab design, and then in the process of slab design, I will come in and finish beam design to BS 8110. So stay tuned as I start introducing you to slab design. So under this topic of slab design, or under the topic of today, I will discuss the following. Number one, the definition of slab, the definition. This is number two, types. Under types, number one, we have one way. Number two, two way. Number three, flat slab. Number four, ribbed. Number five, we have the cantilever. So I will discuss those types in detail. Then after this, I will proceed to something else, that's the design of one-way slab to BS 8110. So after that, this will be the end of today's topic. Design of one-way slab is just an introduction, introducing you to the formulas and the rest, and then we will tackle example in my coming lesson or session. So to begin, I may not know some of you where you are living, but I'm sure some of you are living in a first floor building, others in a second floor building, others in a third floor building, fourth floor, as you go up, even up to 20th floor. So as you come from the job, when you enter into that a small room you are living in, when you step into that room, you step on the surface of that building, and that surface may be made up of tiles, terrazzo, or even wooden surface. So that surface or that tiles, it is attached to a floor, and that floor is made up of slab. So that is what we call a slab. So a slab is a flat horizontal element, usually made of reinforced concrete, that is used to create floor. It can also used to create roofs and ceilings in building and other structures. So this slab, it is made to create a surface so that you can operate on it, and this surface, it transfers loads to beams, to column or walls, depending on types of supports. So slabs carries dead load, its own weight, live load, example, people, furniture, etc., and sometimes additional loads like equipment or snow. Slab thickness. So slab thickness is very important in designing a slab. So for a typical residential ground floor slab, a minimum of 125 mm is often cited, while for heavier loads needs a thicker slab such as 150 mm or more. For example, if you are designing a slab that will carry a water tank, you will design a slab that will have a thickness that will sustain the loading from the water tank and the self weight of that floor slab. So generally it will be something like 150 or above, maybe 200 millimeter. Of course, it's usually 200 millimeter for a slab that is carrying a water tank. Factors influencing slab thickness are loads. How does these loads influence slab thickness? So this require thicker and more robust slab. So if this load is much higher, then it means you will require a thicker and more robust slab. Then you have the building type. Residential, commercial, and industrial building have different loads requirements influencing the necessary slab thickness. And then you have the structural design. So under structural design, the span of the slab and the type of support system, example beams, dictate its thickness. So slabs are designed as a series of shallow rectangular beams. So if these beam series are placed side by side and connected transversely such that it is possible to share the loads between adjacent beams, the combination of the beam will act as a slab, as shown below. So this is the slab and this is the beam. So this beam form the slab. So the design of slabs is similar in principle to that of beams. The major difference is that in slab design, the serviceability state of deflection is normally critical rather than the ultimate limit state of bending and shear as seen in the beam. So let's now proceed to the types of slabs. So number one, we have one-way slab. What is a one-way slab? In this slab, the reinforced concrete slab that primarily transfer loads and bends in only one direction. So the ratio of longer span Ly to shorter span Lx is greater or equal to 2. So it's greater or equal to 2. So in short, Ly over Lx is greater or equal to 2. So for you to determine if a slab is a one-way or a two-way slab, you need to find their ratio, and the ratio is given by Ly over Lx. So if Ly over Lx is greater or equal to 2, then that is a one-way slab. We will see a case for a two-way slab. So in this one, the main bending occurs in Lx direction. So main bending occur in LX direction. So this direction. And then the main steel placed along LX direction. So the main steel reinforcement, main steel placed along LX, and the distribution bar or a secondary bar is placed along LY. So that is all about a one-way slab. Let's proceed to a number 2 type, which is a two-way slab. Number 2 two-way slab, it bends in two directions. It is used when Lx over Ly is less or equal to 2. So the Ly is the longer span and Lx is the shorter span. So this is the plan. As you can see, the load is distributed on the 4 walls of this plan. So this is wall A, wall B, wall C, wall D. Then load on wall A, load on wall C, on wall C, load on wall B, and then load on wall B. So that is all about the two-way slab. We proceed to number 3. At number 3, we have what we call flat slab. So what is a flat slab? A flat slab is a two-way reinforced concrete slab that usually does not have beams and girders, and the loads are transferred directly to column. So this is a plan for flat slab, and this is an elevation. So on this one is the column, and this is what we call the drop panel. So if you come to the section, this is the slab, then the drop panel, and then the column. So a drop panel has several functions on this flat slab. So what is the function of drop panel? Number 1, punching shear resistance. So this drop panel, it helps in punching shear resistance. At the slab column connection, there is high risk of punching shear failure. So here at the column, there is punching shear failure. So to reduce this punching shear failure, you use a drop panel, and this drop panel is other than thickened portion of a flat slab around top of column. So this is just a thickened. The drop panel is a thickened portion of a flat slab around top of a column to prevent punching shear at this column. Then number 2 of drop panel function is to reduce the negative moment at this column, and then it improves load carrying capacity, and then the last one, it reduces deflection. So this drop panel, it reduces deflection in this flat slab. So what are the advantages of flat slab? Number 1, it reduces floor to floor height due to elimination of beams. So as we have been said in this statement, there is an elimination of beams. As you know, beams, it will add the height, the overall height of the floor to floor. So if you eliminate these beams, it means you have reduced the floor height of this structure. So we have said it reduces floor to floor height due to elimination of beams. Then number 2, ease of construction. Number 3, improved use of space. We have the disadvantages. Punching shear problem. It has a punching shear problem, more so at the column. So we introduce the drop panel to resist this punching shear at this column. And then number 2, high deflection. So the flat slab, it is associated with high deflection. Again, the drop panel will reduce this high deflection. And then high reinforcement requirement. Again, it requires a high reinforcement. So this flat slab. So that is all about a flat slab. As you can see, this is the flat slab. So we move to a fourth one, a fourth type of slab. So number 4, we have the hollow core slab. It is a precast or a pre-stressed concrete structural element with continuous void or hollow running through its length. Reduces the overall weight of the slab without compromising its strength. So this is the hollow core slab. This is a section, hollow core slab section. It is good for long spans. We proceed to number 5, ribbed or a waffle slab. So number 5, we have the ribbed slab or the waffle slab. Slab cast with ribs like waffle. So these are the ribs like waffle for strength. Ideal for large span areas like auditorium. So this is the waffle slab cross section. This is how it looks like. We proceed to the last one, which is the cantilever slab. So the cantilever slab, it is supported only on one side. It is used for balconies, projection, etc. So this is a section of a cantilever slab. As you can see, this is the balcony and this is the rest of the slab. So that is all about the types of slab. Design of one-way spanning solid slab. Procedure. Number 1, determine suitable depth of slab. Number 2, calculate main and secondary reinforcement area. Number 3, check critical shear stress. And then the last one, check detailing requirement. So we begin by the depth ratio. So 3.10.2.1 plus 3.5.7 of BS at 110. Solid slabs are designed as if they consist of a series of beams of 1 meter width. The effective span of the slab is taken as the smaller of A, distance between center of bearing A, this is the bearing, so this is the center of the bearing, so this is the distance A, or B, clear distance D, this is the clear distance, plus effective depth D of the slab. So this is the effective depth. It is from the top of the slab to the center of this reinforcement. So D minimum is equal to span over basic ratio times modification factor. The basic ratio, which is span over effective depth ratio, are given in table 3.14. In order to make first estimate of the effective depth D minimum of the slab, a value of say 1.4 is assumed for the modification factor. The main steel can then be calculated and used to determine the actual value of the modification factor. So the main steel can be calculated using section 3.10.2.2. So let's talk about steel area 3.10.2.2. So this one is found in clause 3.5.4 of BS 8110. So the procedure is the overall depth H is determined, then the ultimate design load is calculated using this formula: 1.4 GK dead load plus 1.6 QK imposed load. Then the design moment M is also calculated. MU is also calculated using equation 3.11. This equation is found in section 3.9.11. Then MU is equal to 0.56 FCU BD square. So if MU is greater than M, which will always be the case, then the compression reinforcement will not be required, which imply the area of steel is equal to M over 0.87 FYZ. And the Z is equal to this formula, where K is equal to M over FCU BD square. So how do you obtain the secondary or the distribution steel bus? So these are the formula that will help you to obtain the area of the minimum area for secondary or distribution steel bus. So AS mean is equal to 0.24% of AC when you are using the strength of steel as 240 Newton per millimeter square. And area of steel minimum is equal to 0.13% of AC when you are using the steel strength of 460 Newton per millimeter square, whereby AC is equal to the total area of concrete. So let's talk about shear. So the shear is found in clause 3.5.5 of BS 8110. So shear resistance is generally not a problem in solid slab subjected to uniformly distributed load. Shear reinforcement should not be provided in slab less than 200 mm deep. And in case you want to provide a shear, so the shear stress V is equal to V over BD, then VC is determined using table 3.11 as seen in the design of beams. If V is less than VC, no shear reinforcement is needed. If V is greater than VC, then shear reinforcement should be provided in accordance to table 3.16. So I will show you the table. So this is table 3.18. As you can see, value of V, Newton per millimeter square, area of shear reinforcement to be provided. If V is less than VC, none required. If V is greater than VC but less than VC plus 0.4, minimum link in area where V is greater than VC. That is the formula. And then where V is greater than VC plus 0.4 but less than 0.8 square root of FCU or less than 5 Newton per millimeter square, then you design the link according to that formula. So let's talk about reinforcement detail. So this will be the last item I will be talking about today. So for a reason of durability, the code specifies limit in the respect of number 1, minimum percentage of reinforcement, number 2, spacing of reinforcement, number 3, maximum crack width. So we begin by number 1, reinforcement area. So area of steel should not be less than the following limits. So area of steel should be greater or equal to 0.24% of AC when using the characteristic strength of steel as 240 Newton per millimeter square. And also area of steel should be greater or equal to 0.13% of AC when using Fy as 460, not 260, as 460 Newton per millimeter square, whereby AC is the total area of concrete. Total area of concrete. Again, we have other specific limit. Number 2, we have the spacing of reinforcement, the maximum crack width, curtailment. So I will leave you as an assignment to go and do more research on the spacing of reinforcement, maximum crack width, and also the curtailment of the reinforcement bar. So this is clause 3.1.2 of PA Set 110, reinforcement detail. As you can see, so that one is for crack width and also curtailment of reinforcement. We also have, yes, that is a detailed curtailment of reinforcement. Go and do more research on them. I will end there for today. So in my next session, I will start designing of one-way spanning solid slab. So don't miss my next lesson, and thank you for your time.